Hello everybody, and welcome back to another CIV 398 assignment tutorial. In this tutorial, we're going to be covering assignment 4, question 4, which is our first kind of taste of stress matrices. So questions 1 through 3, they have all been about strain, not too bad. Well, number 3 was a little long, but overall not too bad. But now question 4, we're going to start dipping our toes into the pool of stress. And hopefully this doesn't make you stressed. Yes, that was a terrible pun, but I know you guys like a nice dry humor, so let's get into it. So the question says the Cauchy stress at a point inside a continuum is given by, and as we can see, the stress tensor, or the Cauchy stress tensor, is a simple 3 by 3 matrix, or tensor, and it's symmetric. So those are two kind of nice key things, 3 by 3 and symmetric, and it wants us to determine three things. It says, what is the traction vector on a plane passing through a point and defined by the equation 5x1 plus x2 equals c. It wants us to find the angle between the traction vector and normal to the plane, and the normal and shear stress components acting on the plane, as well as indicating whether the normal stress is in tension or in compression. So, as you guys will see, the only thing that we really need to solve these two questions are two things. The stress tensor, which we're given, it's kind of there, nice big bold stress tensor, and the normal vector to the plane. And you guys are going to be saying, okay, Clayton, well, where's the normal vector? I see I give an equation, 5x1 plus x2 equals c, but I don't actually have a normal vector. So the key to this question, or the only real hard part to this question, is what is the normal vector? Well, in this case, the normal vector is actually can be obtained from the equation. All you do is you take the components in front of the x1, x2, and x3, and that's your normal vector. So in this case, where I got 5x1 plus x2, and technically plus 0x3, my normal vector will be 5, 1, and 0. So that's how you get it. It's really easy if you're given the equation. It's just a little trick. So let's get into actually determining how to solve all these things. So the stress at a point. So far we know that we have a point inside a continuum, and I put it as kind of a rectangle, but let's just pretend that this is a point, and I take a slice. And as you guys know from statics and 270 and everything, is when we cut a material and look inside, it has internal forces. So this is going to be the first part. So first of all, I cut the plane. So I cut it, and I define that cut by my normal vector. Depending on the normal vector, it tells me how I cut the plane, what angle I cut the plane, etc., etc. And as I said, as we cut the plane, we're going to have internal forces. And these are represented by the traction vector, Tn. So the first part of the question wants us to find this traction vector, Tn. Well, all you do to find Tn is you simply take our stress tensor, or stress matrix, that 3 by 3 matrix, and you multiply it by our normal vector. It's as simple as that. A 3 by 3 matrix multiplied by a 3 by 1 vector, that's it, that's all. You'll get your traction vector, Tn. Now, again, this will be a traction vector, and what it's going to ask next in the following parts of the question, it's going to start asking, okay, well, what are the normal stresses and the shear stresses? And you say, okay, well, what exactly does that mean? Well, the normal stress is that part of that stress traction vector, some people also call it a stress vector, but it's basically the component of the traction vector that is in line with the normal vector. And in order to find that, all we have to do is we take our traction vector Tn and we dot it. So there's the key here, we dot it with our normal vector. So again, the traction vector is a vector, the normal vector is a vector, two vectors, we can dot them together, we'll get a single scalar value, which is our normal stress. If it's in tension or compression, well, that has to do with the sign of it. Of course, if it's negative, it's going to be in compression. If it's positive, it's going to be in tension. And as you guys can kind of see from the figure below, we're kind of making a triangle. So if we complete that triangle by adding that other component, that perpendicular component, that's actually our shear stress. And this one's a little bit more complicated to actually calculate, but as you guys will see, it's not too bad. We have our traction vector, which is a vector, minus our normal stress. So here's the key here. That's sigma n, that's our normal stress, that's a scalar value. That is not the Cauchy stress matrix. That's just the normal stress. And then we multiply that by our normal vector. So we have a traction vector, which is a vector, minus a scalar times a vector. Well, that'll give us a vector. So in the end, the shear stress is going to be the norm of a vector. And that vector is Tn minus sigma n times n. So as you guys will see, it's actually not too bad to calculate. But again, I just want to emphasize the traction vector. This will be a vector. The normal stress, this will be a scalar. Because remember, if we dot two things, we're just given a single number. We're not given a vector. And then for the shear stress, we're taking the norm of something, which will result in another scalar value, just a single number. So there's kind of the keys to keep in mind. And from the diagram below, you can kind of see what each one of these represents. Now, one of the questions I got asked already was, how do I find the angle between two vectors? Well, if you guys go back to question 2, I believe, when we're talking about angles, we use that dot product formula. So that dot product formula isn't exclusive to continuum mechanics. That's for any two vectors. So if we want to find the angle between any two vectors, all we have to do is take vector A and vector B, dot them together, divide by the norm of A and the norm of B, and then just inverse cosine it. So if you guys want the dot product formulation, it's back in, I believe, question number 2. You can use that formulation for any angle of any vector, and we can use it here again. So that concludes this question. Again, nice, simple, easy question. We're kind of dipping our toes into the stress pool. Again, should be nice and easy. Stress isn't too bad. It gets a little bit worse later on, but right now you guys should be nice and happy. So thank you guys all so much for listening. I really appreciate it. I will see you guys in question number 5, the bonus question.